Hello, my name is Rucha Rasni. In this video, I shall be covering the basic principle of a spin transfer torque random access memory and its physical implementation. Memory performance is fast becoming the key bottleneck that limits system performance. The system performance is determined by the performance of both the processor and the associated memory. The use of multi-core processors, instruction-level pipelining, and parallelism have resulted in improvement in the processor performance. Request processing time is more often limited by memory or disk performance than by performance of the processor, especially when we consider throughput-oriented workloads. The memory latency thus puts a limit on throughput and latency improvement factor. Also, as we scale down beyond 45 nanometers, there are several problems associated with the existing non-volatile memories. SRAM faces issues like high power consumption and increased leakage. DRAM requires high refresh current and faces compatibility issues. Flash faces issues like increase in write power requirement, reduced performance, limited endurance, and increased complexity of the controller. Thus, arises a need for newer methods of data storage, more so when we consider scalability. What do we design from a memory? Well, ideally, we look for a memory that has high read-write speed, consumes less standby power, infinite endurance, and a compact structure. Well, of course, and low cost. Unlike semiconductor memories that use electron charge to store data, MRAM uses electron spin, and unlike charge, electron spin is inherently permanent. MRAM has been called the ideal memory because of its potential to combine the speed of SRAM, the density of DRAM, and the non-volatility of a flash. MRAMs make use of magnetic tunneling junctions to store data. There are currently 3 magnetic tunneling junction writing approaches: field-induced magnetic switching, thermally assisted switching, and spin transfer torque. The high switching current requirement of the first 2 writing approaches limits its applications. Hence, the second generation of MRAMs implement spin transfer torque. A magnetic tunneling junction consists of 2 ferromagnetic layers separated by a dielectric called spacer. This thin insulating layer is usually made up of magnesium oxide. The magnetization of one ferromagnetic layer is fixed, while the magnetization of the other layer is controlled by injecting spin-polarized electrons. A magnetic tunneling junction behaves as a resistor with 2 resistance values, high and low, depending on the magnetization direction in the 2 ferromagnetic layers. If the spin transport is in the same direction in both ferromagnetic layers, the MTJ presents a low resistance and is designated a binary value of 0. A high resistance is seen when the spin direction in both ferromagnetic layers is opposite or antiparallel. This orientation corresponds to a binary value of 1. So, in STT-RAM, data is read as tunnel junction resistance. The resistance can be easily implemented using a differential sense amplifier at low cost. Data write in STT-RAM is achieved by passing a spin-polarized current through the tunnel junction. The tunnel barrier is as thin as a few atomic layers. Depending on spin polarizations, electrons tunnel through the thin normally insulated material, causing a resistance change. Threshold current density required for switching MTJ state is named as critical current density. The direction of the current determines the MTJ state change from parallel to antiparallel or antiparallel to parallel. This critical current density has been found to be as low as 0.8 microamps per centimeter square. As the dimensions of the MTJ is very small, a critical current of about 100 microamps would suffice to change the state of the MTJ. This value of current can be easily generated by small transistors. A 1 transistor 1 MTJ per cell structure is as shown. It consists of 1 MTJ and 1 NMOS transistor. All the cells on each bit line or BL share a reference cell that consists of one PMOS transistor and one reference resistor with the resistance of RH plus RL by 2, where RH refers to the high resistance that is achieved when the orientation of the MTJ is antiparallel. RL, on the other hand, corresponds to the value of the resistance when the two ferromagnetic layers' spin directions are parallel. The NMOS transistor in each cell should be sized according to the STT write current threshold. During the read operation, the PMOS transistor in the reference cell is turned on so that the reference cell and the selected cell forms a voltage divider through the bit line. A differential cell's amplifier is implemented on the bit line to read the resistance value. RH and RL of the MTJs fall into the range of 5 to 6 kiloohms and 2 to 3 kiloohms, respectively. Figure shows an STT-RAM array consisting of 4 cells. Let us now look at the operation of an STT-RAM cell. The read operation consists of 3 phases as follows. Similar to SRAM and DRAM design, pre-charge the bit lines to medium voltage. Then, turn on the reference cell and the selected cell to form a voltage divider along the bit line. Depending on the resistance of the MTJ in selected cell, the voltage divider will start to charge or discharge the bit line. After a pre-specified sensing time, turn on the differential amplifier to generate the read output by comparing the bit line voltage and the pre-charge voltage. For writes, during antiparallel to parallel switching, that is, to write to 0, the current flows from the bit line to the source line. The initial cell resistance is RH. During parallel to antiparallel switching, that is, to write 1, the current flows from the source line to the bit line. The MTJ acts as a resistor at the source of the transistor, thereby reducing its effective gate-to-source voltage. Further, during this operation, the initial cell resistance is RL. The write current threshold is as low as a few hundred microamps, which directly enables a significant reduction of memory write compared with traditional magnetoresistive memories. Let us now see the advantages and disadvantages of replacing a DRAM with SRAM. The advantages include non-volatility, high scalability, and lower power consumption. The disadvantage, on the other hand, is that the STT-RAM uses higher write energy than DRAMs do, and as of now, the STT-RAM is still under development, so we cannot for sure say that the pros can be proven. If we replace SRAMs with STT-RAMs, the advantages are non-volatility, high scalability, and low power consumption, higher density as well. On the other hand, the cons include slower write time and higher write current. Non-volatile STT-RAMs is a new technology that combines the capacity and cost benefits of DRAM, the fast read and write performance of SRAM, and the non-volatility of flash with essentially unlimited endurance. It has excellent write selectivity, excellent scalability beyond the 45 nanometer technology, low power consumption, and a simpler architecture. It also has a simpler manufacturing process than the first generation field switch MRAMs. Everspin has developed a 64 megabyte STT-RAM DDR3. It combines the speed and endurance of DRAM with the persistence of NAND, creating an almost perfect storage medium. Unfortunately, the technology is currently in the beginning stages of adoption. Thus, cost and capacity are inhibiting mass deployment. STT-RAM is proven and is effective, and it eliminates the need for power fail capacitors. STT-RAM has immense potential for future development. These are my references. Thank you.